Thanks, Katya. I'd like to begin by thanking Katya for the kind invitation to this seminar. I've been an occasional visitor to this seminar throughout the COVID era, and it's been one of the things that's really held the community together, I think. It's been really terrific. Um, I should begin by explaining, just in case it wasn't completely apparent from my title and abstract, that this is not actually an inverse problems talk. I'm not actually an inverse problems researcher, but it's at least sort of in allied areas of applied mathematics. And so I'm hoping it will be of interest. So this is joint work with David Lafontaine and Ewan Spence, what I'm going to talk about. And it's part of a kind of a larger series of projects that we've had together to try to apply the methods of semi-classical microlocal analysis to outstanding open problems in understanding the numerical analysis of the Helmholtz equation. So let me begin with my setup. What do I mean by the Helmholtz equation, for starters? So let's begin by just working on RD, flat RD, and I take the standard Laplacian with the sort of usual analyst sign convention. That's a negative definite operator. And I'm solving the equation Laplacian plus k squared u is some inhomogeneity. Let's take it to be compactly supported forever in this talk, just in case I forget to say that later. So say L2 and compactly supported. And the solutions to this equation you can think of, if you prefer evolution equations, as describing time harmonic solutions to the wave equation, because of course e to the plus or minus I kt times u is then a solution to the wave equation. Okay, so it's the stationary version of the wave equation. It's what you get if you formally Fourier transform it in time. This is of considerable interest in numerical analysis. We're interested in trying to approximate solutions to this equation. And we're interested in doing so uniformly in some sense as k, the wave number, gets big, high frequency waves. So I would add that if I fix a k, then I can essentially think of this as a perturbation of the Poisson equation, which is a very well studied thing in its own right and in many respects better understood. But the difficulties, the main difficulties in this talk are about what happens as k goes to infinity. So this could model problems in acoustics, where you've got a high frequency acoustical wave bouncing around or a standing wave, I should say. Or it could model some caricature of problems in electromagnetism, of course, where we've forgotten about a lot of the subtleties of polarization. So there's a lot of null space of Laplacian plus k squared, so I need to say a little bit more about what solution to this equation do I mean. There are lots. And the usual thing in the scattering theory business is to take the solution that solves the Sommerfeld radiation condition, which I've written here. If you're not familiar with this, you should just think that this encodes the idea that the solution is radiating energy outward, from outward toward infinity from whatever interaction region you might have. Okay, and so why this? Well, on the wave equation side, you might be interested in solving forward in time with compactly supported initial data, and these are essentially the solutions that arise when you're studying that forward wave equation. Now, I stated this in flat space, but the problem gets much more interesting if I introduce geometry. Of course, I should point out, going back for a moment, this flat space solution can be easily solved by Fourier analysis. So that's a little too easy. Things get considerably harder as soon as you consider variable media. So I could, for example, consider an inhomogeneous anisotropic medium where I've got a variable, so let's say sound speed or wave speed c, which is a function of x, and maybe an anisotropy encoded by this tensor a. I'm going to assume throughout, though, that outside a compact set, my problem really is the flat Laplacian. It is the standard Helmholtz operator, and so c equals 1 and a is the identity outside some big compact set. If, like me, you were brought up more as a geometer than a practical analyst, you might prefer to think of the Laplace-Beltrami operator with respect to a Riemannian metric, which is up to some conjugation, essentially the same thing. Okay. No matter what, I'll write the operator the same way as the Laplace operator. So you could also introduce a boundary problem. One of the most important practical problems, of course, is to study these waves bouncing around in the exterior of one or more obstacles. So you could have an obstacle, say with Dirichlet boundary condition, and then also have variable coefficients outside of it, the way I've described. And I don't want to emphasize this in this talk, but some of the results we have apply in part to transmission problems, where you've got a kind of a penetrable obstacle, which means that your coefficients are smooth, say, except that they jump across a hypersurface, let's say. Now I'm sort of paying lip service to the idea that this has something to do with scattering theory, and I'm not going to go too far down that road, but I will say that a very closely related problem is if instead you want to solve the homogeneous Helmholtz equation, so an actual solution to Laplacian plus k squared u equals 0, but instead of insisting that the solution be outgoing, which would then be asking too much, it turns out, that would make it 0, you ask that the solution be some incident wave that you've specified plus an outgoing solution. And so I have a picture of that here. It's a very closely related problem, and I won't talk about it explicitly, but essentially can be analyzed once you can analyze the inhomogeneous problem. So here's a picture. We've got these two obstacles in the plane. We've illuminated them by a plane wave and computed the scattered field. I say we, but actually I had nothing to do with this. This is Chandler, Wild, Graham, Langdon, and Spence. I should say, for those of you who don't know me personally, I'm not a numerical analyst by training. This is all news to me. Part of the adventure for me is to try to understand how people make pictures like this. And so I'm going to begin by giving the pure mathematician's explanation in a nutshell of how numerical analysts make these cool pictures. So I thought that was pretty cool to learn. So what do you do? So the first step is to recast your problem essentially in a kind of a distributional or weak formulation. So instead of considering Laplacian plus k squared, I take the quadratic form associated with Laplacian plus k squared. I formally integrate by parts. I take the L2 inner product of Laplacian plus k squared u equals v. I think I've slipped a minus sign in here. That is this integral. And so loosely speaking, to solve the Helmholtz equation, you want it to be the case that for every test function v, this should be the same as the pairing of minus f with v in the L2 sense, which I've written here. Now there's a slight subtlety, which is that I was asking about outgoing solutions. Now the Sommerfeld radiation condition you should think of as a kind of boundary condition at infinity. It says asymptotically the solution is going out. But there's a nice trick that the numerical analysts use to bring that boundary condition from infinity in to the boundary of a finite ball, so that you've got an actual problem that's posed on a compact set. And that's the following. You use the exterior Dirichlet-Neumann operator for the ball. So what does this guy do? It takes a function on the sphere, on a large sphere of radius r, and considers that as Dirichlet data for an outgoing solution to the Helmholtz equation exterior to the ball, and it maps it to the Neumann data, okay, the exterior Dirichlet-Neumann operator. And it turns out that if you do the integration by parts, if you have a Helmholtz solution, this is what you get as the boundary term on the ball, on the boundary of the ball. And so solving this turns out to be equivalent to solving the original problem with the Sommerfeld radiation condition. So you replace the Sommerfeld condition by what turns out to be a somewhat awkwardly non-local boundary condition on the boundary of the ball of radius r. So that's the bad news in a way. It's a slightly complicated operator, but it's completely explicit, right? This is the exterior of the ball in flat space. This was supposed to be some large ball that's outside of where anything interesting is happening with obstacles or coefficients. So this is a model problem for the exterior of the ball in flat space. You solve it using Bessel functions. This is a completely explicit thing. There's a certain amount of pre-computation you can do, I think, to implement this. And so I'm going to take this as just something we can easily compute. In practice, it turns out numerical analysts aren't super happy about this operator, and there are various, because it is a little bit expensive, I think, to implement, there are various methods for trying to replace that thing with something cheaper, but that's a subject for another talk. So anyway, we've recast our original problem about solving the Helmholtz equation for outgoing things with a problem that's in weak form, where we've got this pairing equaling the L2 pairing of our inhomogeneity with our test function. So it's a weak formulation. And now, how do we solve numerically? How do we reduce this to a finite dimensional problem that we might hope to solve on a computer? Well, we use the Galerkin method. So what is that? So this was posed on H1. So the original problem was to find a solution in H1, and this was the variational formulation of that. So instead of working in H1, I take a sequence of finite dimensional subspaces of H1. And you should imagine that I've chosen these in some clever way so that as n, this parameter, gets big, these subspaces are getting bigger and bigger and bigger and coming closer to being all of H1. There are, in particular, things in H1 can be better and better approximated by things in these subspaces. So what do I do? For each of those subspaces, I can pose the same variational problem. It makes sense. I can ask that this inner product, that this pairing, this bilinear pairing, equal the L2 pairing of f with a test function in my subspace. So that makes sense on any subspace of H1. So that's now a linear algebra problem. If I've found a finite dimensional subspace, I can pose this linear algebra problem on that subspace, and I can try to find this u. This un, that is, that depends on the subspace. So how do you choose your subspaces? Well, there's a lot of art to that, and there are many choices. But a common choice is to do the following. We create a mesh. We triangulate our large ball. This doesn't look like a ball, but it was supposed to be a ball, I think. It got distorted. Maybe exterior to some obstacle. We triangulate it with tetrahedra of size of order hn, where hn is an independent number, or I'll call it h later on, and it's getting small. You think of it as a fine triangulation. And then you let Vn, the subspace of H1, be the space of H1 functions that are piecewise polynomials on these mesh elements, on this triangulation, and that match up along the edges in such a way that they are in H1. So they should be continuous in particular. So this was already interesting when P is 1. So think about that for a start. You just take piecewise linear things fitted together along these edges. And that's your subspace. And you can make a sequence of subspaces by shrinking the mesh size and refining things. You could also make a sequence of subspaces by increasing the polynomial degree, if you were so inclined. So when you apply the Galerkin method this way, so you've got a finite dimensional subspace and then a solution in the subspace that's supposed to approximate your real guy, that's called the finite element method. That's what FEM is. Any questions, by the way? So this was my, 5-minute synopsis of how do you do numerical analysis.
So what is the size of an element? I mean, they have different shapes.
Yeah, okay, so let's say the diameter. And I admit that I put this picture in because I thought it was cool, but it doesn't actually illustrate what I said very well because the size in what I've said is supposed to be roughly uniform, whereas this one seems to be an adaptive grid that's been refined at some of the, at corner points or something. So it's a bit of a cheat. Yeah, let's say the maximum diameter of the elements is shrinking. That's all I'm asking.
Okay.
Other questions? Okay, so I said you could improve yourself. You could get a better approximation of H1. Let's say by shrinking the mesh size H, and that process of getting better and better approximations to your solution, you hope, is called HFEM. Okay, so we fix the polynomial degree in this, and 1 would do fine for a start. In costing that out and figuring out how much work that's going to involve, it's useful to keep track of the number of degrees of freedom for the finite dimensional problem. And if you cost it out, that's P, the polynomial degree, divided by the mesh size to the dimension. That's roughly how big it is. So that's the finite element method. The next question you might ask is, does it work? So let's suppose I've chosen these VNs, these subspaces, and I claim I have in this mesh by making these decisions about refining a mesh. Suppose you've chosen it so that you can get better and better approximations to any element in H1 by taking the closest point in these Galerkin subspaces. Okay, so the finite element method almost certainly doesn't choose those optimal approximations. There's no earthly reason the FEM should miraculously manage to produce the closest element in Vn to the true solution. Okay, there is some closest element. You don't know what it is because you don't know the true solution in particular. So so one basic requirement you might like for your method is what's called quasi-optimality, which says, well, okay, the distance from the true solution of my FEM solution, of my Galerkin solution, is no bigger than a fixed multiple c of the distance of the optimal one to my true solution. So you're only off by a fixed factor in relative to the best possible approximation in Vn. So this is a sort of basic thing you'd want, and the big question for us is, can we get this basic thing to hold in some uniform way for k big, or what can we do that guarantees that this will hold, that is varying in an appropriate way as k goes to infinity? How do we make this work for k big? You might object that this wasn't really the estimate you wanted. You really wanted the distance from your Galerkin guy to the true guy to be small. And that would be called a relative error estimate. And I'll just say that this can be upgraded to a relative error estimate relatively easily, because that's just a matter of knowing that the VNs are indeed filling out H1, so that these closest elements are indeed getting small. So for this talk, we're going to focus on quasi-optimality, but you could ask for different kinds of error estimates, and they're closely related. So what's known? So going back to Eilenberg and Babushka, for polynomial degree 1, for piecewise linear things, this quasi-optimality is known to hold uniformly in k, as long as this condition is satisfied. Hk squared is sufficiently small. H is the mesh size, remember, and k is the frequency parameter. So if you cost that out, according to my formula for degrees of freedom, that's k to the 2d degrees of freedom. So if you're in 3 dimensions, k to the 6th. It's quite a large polynomial number of degrees of freedom as k goes to infinity. And I'll just say that heuristically, you might think you should be able to do much better. So why is that? Well, you know, what's the prototypical solution to the Helmholtz equation, right? It's a plane wave oscillating with frequency k, which I've just drawn very poorly. So that oscillates on a scale, on a length scale of 1 over k. So if my mesh size is sufficiently small compared to 1 over k, you should be able to distinguish those oscillations. You could make a perfectly reasonable approximation to a plane wave like this by using a mesh size that was small on the scale of 1 over k. So you might hope that h times k small would suffice, that h really needs to be like 1 over k. And that's famously wrong. So there's this paper by Eilenberg and Babushka from 1995. As of when I checked a few days ago, it had 800 citations. It's been incredibly influential. They explain what they call the pollution effect, which is that they can show quasi-optimality fails for sure, even in a simple one-dimensional example, when you only assume that k is of order, that h is of order k inverse. So it doesn't suffice to shrink your mesh to be small on the scale just of one wavelength. It's not enough. So that's the bad news. The good news is there are some relatively reasonable fixes that recover quasi-optimality. And so in particular, I'm going to describe this work of Melenk and Sauter from 2010 and 2011, which has a beautiful workaround. The workaround is that you shouldn't just use HFEM, where you try to get a better approximation by shrinking the mesh size. You should do something else simultaneously. You should also increase the polynomial degree. Now that's of course costly, but it turns out you're not going to need to do that very much. So Melenk and Sauter were able to show that in certain special cases, they could recover quasi-optimality when not just hk is sufficiently small, but even hk over p, the polynomial degree, is sufficiently small. So that's much better than hk squared small. You've got not just hk, but the p is helping you. The cost is you have to increase p, but p is supposed to increase only logarithmically in the wave number. So the main takeaway actually is that here you've got hk rather than hk squared, but this p in the denominator, which is like log k, is also helping you a little bit too. And there's this price that you have to logarithmically increase the degree. So a very important consequence is that if you count up degrees of freedom here, you're back to k to the d degrees of freedom. Much better than the k to the 2d we had before from Eilenberg and Babushka. Okay. So that's pretty good. By the way, in passing, I'm told that in real solvers, and probably one of the numerical analysts who's here can correct me if I'm wrong, but I'm told that in real solvers, it's not actually the case that you sort of turn some crank and you keep increasing p and increasing p and increasing p. In practice, you might just fix a p that was big thought to be big enough for your problem, and p is like 10 or 15 is like enough. That's as high as anyone ever goes. So log of the wave number is like 10 or 15 in practice, I guess. So what cases were they able to cover? Malenk and Sauter were only able to show this in certain special geometric cases. So one was just the simplest problem that you could solve by Fourier analysis in the first place, that the actual Laplacian plus k squared u equals 0, where that's the flat Laplacian 0, I'll call it. Okay, the ordinary Laplacian. But then they could also deal with certain kinds of boundary problems. They could deal with the exterior of an analytic obstacle or an analytic polygon with a Dirichlet boundary condition. But the coefficients have to be constant. They still have to be constant coefficient. And they needed what's called a polynomial resolvent estimate. So this is going to be an assumption throughout what I'm going to talk about, and I will say more about it later. But just in brief, it says that if I solve the Helmholtz equation for u in terms of f, so I've got Laplacian plus k squared u equals f. And if I localize u, I'm only concerned with a local problem, then I can bound the L2 norm in terms of f in a way that grows at worst polynomially in the frequency. So I will talk more about that assumption, which is a serious assumption, a little later. For the experts, I'll remind you that certainly that would hold a fortiori if the obstacles were non-trapping. And I'll explain what that means later. So the main theorem I want to state today is that we can recover the results of Malenk and Sauter, more or less, in much broader geometric generality. So the first theorem I want to state is that their result holds perfectly nicely with variable coefficients. They only need to be C infinity, no analyticity needed, but this is in the case where there's no obstacle. We require the same polynomial resolvent estimate. Okay, but we get quasi-optimality under these same conditions on hk and p, which is that hk over p is small, p grows logarithmically. The second part is a part that holds for the obstacle problem, and so we again need analyticity of the obstacle. We can have variable coefficients, but they have to be analytic near the obstacle. There still has to be a polynomial resolvent estimate, and we get quasi-optimality under almost the same conditions of Malenk and Sauter. Just to remind you, they had a p in this denominator helping them out, and we don't. Okay, and if you count degrees of freedom, we're not far off that k to the d. We lose a log k to the d relative to the optimal thing. I will add at this point actually that we have work in progress joint with Jeff Galkowski to try to upgrade this to get that 1 over p in that denominator. We think we know how to do that, but it's a little technically fussy. And we have some related results for transparent obstacles that aren't really about HP fem, but are about what happens when you do H fem, but you fix a large p. So I'm not going to talk about those. So I'll tell you a little about how those results are proved. There's a lot of pieces in this, and some of them are pieces that delve deep into issues of polynomial approximation, in which I'm not expert, and which I've always treated as a black box. So I'll tell you what they are, but I can't answer questions about them, I warn you. So the main ingredient in this is an estimate on the adjoint problem. So the Helmholtz equation, it's self-adjoint, right? The Helmholtz operator is self-adjoint. So you think the adjoint problem is the original problem. But of course, I imposed this radiation condition, which has a factor of I in it. And so if you formally adjointify, you get a different problem, actually, which is the Helmholtz equation with the incoming Sommerfeld radiation condition. So up to a complex conjugate, it's the same as the original problem. So I'm not going to make too much of that distinction, but technically it's the adjoint problem. And so let me let S star be the solution operator to the adjoint problem. So S star solves Laplacian plus k squared u equals f u incoming, so satisfies the incoming Sommerfeld radiation condition. We say u is S star of f. Okay. And then we define these adjoint approximability constants. So you say I solve the Helmholtz equation, and I then want to approximate by something in my Galerkin subspace, and I want to see how well I can do at doing that in some appropriate norm relative to the size of my data f. So I normalize by that. And I define this constant which tells me how well I can do that. That's eta of Vn. So it tells me how well does Vn allow me to approximate solutions in the adjoint problem. What is this norm? It's more or less the H1 norm, but it's got a scaling in it of k squared here. If you're a semi-classical analyst, you'll recognize this is essentially a semi-classical Sobolev space. But let me just point out that if I take something like e to the ikx, a plane wave, then the gradient of u is comparable to k squared times the L2 norm. The L2 norm of the gradient is comparable to k squared times the L2 norm. This is the right scaling to make those two terms of roughly the same size. Okay, so eta measures how well solutions to the adjoint problem are approximated in Galerkin subspaces. And there's a known condition for quasi-optimality, which is that k times eta should be sufficiently small. Now the argument for this is quite beautiful. It goes back to Schatz in 1974. I have a slide on it at the end in case anyone wants to see it. If I do it, I'll bog down probably, and I'll have showed you something beautiful, but I won't get to the end of my talk. So I'll put up that slide at the end if there's demand. Okay, but we're going to take for granted this assertion that if k eta is sufficiently small, we get quasi-optimality. Now, how would you make k eta small? Well, you want to make eta small. And how do you make eta small? Well, you get good estimates if you have good estimates on S star f in some appropriate spaces, right? How well can I approximate S star f by elements of my Galerkin subspace? Well, here's what Malenk and Sauter do to approximate it. They split it into two pieces. So the splitting is as follows. The two pieces are called UA and UH2. I think this is their notation. UA is called UA because it's analytic. It took me a while to wrap my mind around the fact that analyticity was really relevant to numerical analysis, because I think of analyticity as something that is numerically very unstable and not a good idea for computation somehow. But the point of analyticity here, the takeaway is, if you're analytic, you have estimates on high derivatives. And part of the package here is there are explicit estimates on high derivatives. How does the alpha derivative grow? And how does that growth involve k, the frequency parameter? So it's analytic with explicit Cauchy estimates. If you like, it's something about the size of the radius of analyticity. And if you have good derivative estimates, you can be better approximated by high degree polynomials. Okay, so that's the numerical analytic black box that I can't open for you. So it's a fact that if I want to use a Galerkin subspace of high degree polynomials, and I have something that I have a function u on which I have good high derivative estimates, I can get a better approximation in H1. And there are a lot of known theorems along those lines. So this analytic part is good because it has these high derivative estimates. It can be very well approximated by high degree polynomials. How about the other part, UH2? So don't take the H2 too seriously. It is called UH2 because it satisfies a good H2 estimate. But what's already interesting is what L2 estimate it satisfies. So forget about these derivatives for a moment. Take alpha equals 0. This says that the L2 norm of this piece goes like k to the minus 2 times the L2 norm of f. Now, if you're familiar with resolvent estimates in scattering theory, you might know that the best I could really hope for as an estimate on u itself, my overall function, would be k inverse. That's already the best that's already what's true in flat Euclidean space. You're never going to get a better estimate of u in terms of f than k inverse. So this says there's 1 power better. That's all. It's just smaller as k goes to infinity. And okay, not only is there 1 power better, but then derivatives behave in an appropriate way. Each derivative costs you a power of k, and you can have up to 2 derivatives. So it's an appropriate semi-classical H2 estimate. Okay, but the main thing is this piece is small. It's smaller than you would expect as k goes to infinity. So I've got these two pieces. The analytic one is exceptionally well approximated because it has good derivative estimates, and this other piece is exceptionally well approximated, well, because it's small. It's essentially an error term. So the main content of our work is to show how to split, how to accomplish this splitting in a wider variety of settings than Malenk and Sauter. So we've reduced to the problem, I claim, of showing that if I solve the Helmholtz equation, I can split the solution into an analytic piece with good derivative estimates that are appropriately uniform in K, and a small piece. And here's how we do it. The principle is very simple. We just use the functional calculus for the self-adjoint operator h bar squared Laplacian. So here's where I become a semiclassical analyst. H bar is K inverse. It's been one of the major problems in our collaboration that bedevils applying semiclassical analysis to numerical analysis is that H is the mesh size, so we can't call it the semiclassical parameter H. So in this talk and in our paper, the semiclassical parameter is H bar. Don't confuse it with the mesh size. They're not directly related. Okay, H is the mesh size, H bar is 1 over K. So I rewrite my equation this way, mostly just because I'm used to writing things that way. And I want to try to take a function of h bar squared Laplacian, k to the minus 2 Laplacian. And well, it's a self-adjoint operator, so I have the spectral theorem on my side. I can take a function of it, just using the functional calculus given to me by the spectral theorem. So what I do is I pick a cutoff, chi L. I'll call it, L is for low. Here's chi L. And it lives out near out in some big interval up to some number lambda, but we won't be too fussy about that. And how am I going to split? I haven't emphasized this, but the splitting really only needs to be local. So I localize u by multiplying it by a cutoff function. That's important because I need to be in L2. And then I apply this function of minus h squared Laplacian. So you should think of that as a spectral localizer. It's localizing in the spectrum of the Laplacian. And this is all that UA is. It's the low frequency spectral part of U locally. And UH2, that's the high frequency part. Chi H is 1 minus chi L. It's the rest. And so as I'll explain in a moment, what this is roughly doing is splitting into frequencies above and below lambda K, where lambda was where this cutoff lives. Okay, so you should think I'm in Fourier domain, if you like, I'm splitting into frequencies above and below lambda K. And you can see that very explicitly if you take the flat Laplacian, because then the functional calculus is very easy to implement, right? The Laplacian's a Fourier multiplier by xi squared, and so functions of it are just functions of xi squared on the Fourier side. So my analytic part is obtained by localizing u, Fourier transforming, and then multiplying by a cutoff function of xi squared over k squared, and inverse Fourier transforming it. So this thing lives where xi is less than k lambda. Okay, so in Fourier domain, that's where you live. You get to have more and more frequencies as k goes to infinity, but you're always cutting off at a frequency parameter comparable to and somewhat bigger than k. Why is this UA a good thing? Well, it's the inverse Fourier transform now of something compactly supported in xi. If I fix k, it's compactly supported in xi. And so it's analytic. It's the inverse Fourier transform of a compactly supported function. Great. And it's easy to see how big derivatives of it are. If we differentiate, that becomes multiplying by xi under the Fourier transform. Well, xi is bounded on the support of this thing. It's bounded by a multiple of k. So every derivative essentially just costs you a multiple of k. So if I want alpha derivatives, I pull down k to the alpha times a constant to the alpha. And that's the desired estimates. That's actually better than the desired estimates. That's a kind of best case scenario here. Except for one thing. These are estimates in terms of phi u, and I wanted my estimates to be in terms of f, the inhomogeneity in the Helmholtz equation. So of course the last step is to estimate phi u in terms of f, and that's one place where my resolvent estimate comes in. I have to have some a priori knowledge of overall how big is u in terms of f. And so I will use that there. Okay, so that was the flat Laplacian. That all works perfectly well if you're on flat Rn. But what if you have variable coefficients or obstacles? The Fourier multiplier strategy instantly gets a little dicier. So remember, we're still going to use the functional calculus, but now it's the functional calculus for a variable coefficient Laplacian. And so things aren't given by Fourier multipliers anymore. So our strategy is as follows. If I have this UA, remember UA is this low frequency cutoff of the Laplacian applied to phi u, locally u. Well, the nice thing about this is that on the support of chi L, I can take an exponentially growing function of S. Let's say chi L of is thought of as a function of S. Chi L of S times e to the ts is bounded. For every t, that's a bounded function of S. And so if I take that function of the operator, it's a bounded operator on L2. So that says that I can apply this operator to UA, and I still get something that's L2 bounded, just because the exponential function is bounded on chi L. But then you recognize that this operator is the backwards evolution operator for the heat equation. So one thing about this spectrally localized thing, I guarantee that I can apply backwards heat evolution, actually for any finite time I want. So okay, so if I tell you I can apply the backwards heat evolution and end up in L2, I can repackage that. I can say, well, I was in the range of the forward heat evolution on L2. Now what happens if I take an L2 function and I evolve it according to the heat equation, maybe for some complicated elliptic operator? Well, if the coefficients are analytic, it's known that it instantly becomes analytic. And in fact, there are known estimates on how that analyticity behaves, how the Cauchy estimates behave as the evolution time goes down to 0. It, of course, goes back to being merely L2 as time goes to 0. So there's a controlled degeneration of the Cauchy estimates as t goes to 0. Fortunately for us, these have been worked out in the heat equation literature by these authors, among others. We get good analytic estimates for UA based on the fact that it's in the forward range of the heat evolution on L2. And this, I claim, gives the analyticity estimates that we wanted. Any questions before I go on? Okay. So what about this other part, the part that was called the H2 part, but really is just the small part? So this was the high frequency part. Why should it satisfy a better estimate than U does in terms of F? And the answer is simple if you're a microlocal analyst. The answer is this is living where your operator, h squared Laplacian plus 1, was semi-classically elliptic. But I can phrase it actually at this level in terms of the functional calculus. So I had the equation h bar squared Laplacian plus 1 equals h bar squared f after my change of parameter there. H bar is 1 over k, remember. And I just apply the spectral cutoff chi h to both sides, and it commutes with other functions of h bar squared Laplacian, in particular with the operator itself. So I move it in there. And now I claim I can invert h bar squared plus 1 on both sides, just because this is what function of h bar squared Laplacian. It's the function minus s plus 1 of that. And that's never 0 on the support of chi h. The support of chi h was chosen to be out beyond 1, right? Here's 1. Here's this lambda where chi h turns on, roughly. That's out here. Here's chi h. And so 1 minus s is never 0, so I can divide by it. And so correspondingly, I can apply the inverse of this operator to both sides, and it behaves as a bounded operator. Just from pure spectral theory. Nothing serious. It's soft. So I get an estimate for the left-hand side in terms of h bar squared f, which I claim is 1 power better than you deserved. And so that's how you get your estimate on this high frequency part. So it's a kind of abstract microlocal elliptic regularity. It's just in terms of the functional calculus. I just said I could divide by this operator because it was a nice function, a nice non-vanishing function of h squared Laplacian. But there's some fine print. So I was applying this stuff to U, and U isn't in L2. Okay, U is some global oscillatory thing. I should localize U, but then I don't satisfy the Helmholtz equation anymore. There's a commutator term. So I'm not going to delve too much into technicalities, but this one is an important one. I get a commutator term here that it turns out I have to estimate. So I'd like to pass the operator through onto U to get an F. I wanted to pass h squared Laplacian plus 1 onto F the way I did before, but I can't. There was a phi in the way. I can't pass it onto U. So I get this. And I need to have some kind of good estimates for that operator. And that gets a little more serious because this thing I can't easily describe in terms of the spectral functional calculus, this commutator term. It's some differential operator with compact support, but it's not a nice function of h squared Laplacian. So here's where I actually need to know something about pseudo-differential operators. There's a beautiful theorem in this context due to Helfer-Robert and Helfer-Sjöstrand that tells me that this thing is in fact a nice semi-classical pseudo-differential operator, meaning you can think of it as a function of h d by dx, essentially, of h bar d by dx. And it's this function of h bar d by dx to top order. This is its principal symbol. And so it turns out that I now need to use honest elliptic regularity. My original operator is elliptic on the microsupport of that operator. And so I can do this same dividing trick with this term, or if you like, what it means is I can factor out a copy of h bar squared Laplacian plus 1 here at the cost of some other nice bounded operator q. I can factor that out, and then when this hits u, I get f. So I get a nice estimate in terms of f again. So that's a little bit of the technical flavor of why the actual microlocal techniques come into play. We need to essentially understand the Schwarz kernel of this spectral cutoff very well. And now finally I want to talk about resolvent estimates. I've been promising you all along a further explanation of these polynomial resolvent estimates, whether you should expect them and why you should care. So in all these microlocal constructions, as well as in estimating that analytic term, I need some kind of estimate that tells me that U is bounded by a polynomial in K times F. In particular, all those microlocal constructions kick off error terms that are known to be rapidly decreasing in K, but that wouldn't be enough if U were say, exponentially growing in K. So rapid decrease is only success if I have some a priori polynomial estimate for the behavior of U locally in terms of the L2 norm of F. Now, it's well known that there are settings where an exponential bound is all you got. So, in cases where there's trapping of classical trajectories, such as this guy, where say a billiard ball can bounce back and forth between the top and bottom of this cavity, and indeed do so in a rather stable fashion so that a perturbation of the original trajectory still stays trapped. It's known by work going back to Burke and Cardozo-Popov, I think, that U is exponentially bounded in terms of F, but no better. No better. So that's bad. By contrast, though, it turns out that if there are no trapped rays, if every billiard trajectory, which is moving, so it's supposed to move along a geodesic for the metric or for the coefficients, for the coefficient matrix, if there's variable coefficients, but I'm going to call it a billiard trajectory, moves along geodesics and reflects off obstacles according to Snell's law. If every one of those rays escapes, if none of them stays trapped forever, then it's known that I get this estimate with a 1 over k in it. So that's certainly polynomially bounded. Indeed, it's got decay. This estimate has a long history, especially in the obstacle problem. It took the combined efforts of quite a few people in the 1980s to understand what we mean, in fact, by a billiard trajectory and how this is connected to the energy decay for the wave equation. I probably also should have added Weinberg, now that I come to think of it, for that latter statement. How is it connected to decay? Okay. So what other situations can we deal with? Well, this is a whole industry, and I'm not going to get too deep into this. If you have, for example, two convex obstacles sufficiently far apart, it's a famous theorem of Ikawa that while there's a trapped trajectory that bounces back and forth between them, because it's so unstable, you only lose just a little, a logarithm, relative to this non-trapping estimate. So that's certainly still polynomially bounded. And then there are many modern results in which hyperbolic dynamics on trapped sets in general guarantees you log loss essentially in this. So those are very mildly trapping, and therefore certainly enjoy the polynomial decay estimate. Hans Christensen and I also exhibited a family of examples where you can get various powers of k occurring on the right. You might think, well, could I only have a log loss or an exponential growth? Well, no, we can get all kinds of different polynomials occurring there, but admittedly by somewhat contrived examples involving degenerate hyperbolic trapping. So I want to end by doing a little bit of publicity for a recent result that says that actually you can mostly get away with polynomial resolvent bounds in practice. Apparently it was well known to the numerical guys that they would take these trapping situations and they would run their codes and nothing would go wrong. And whereas you would think, based on the failure of the resolvent estimates, that it should be a catastrophe. And so that was some piece of evidence for the following theorem. A more stronger piece of evidence was an actual theorem of Kaptebask involving a special example of transparent obstacles with trapping, where he did a ball in R3, a partly transparent ball in R3, and worked it out completely in terms of Bessel functions and found something similar. And especially since he's on the call, I should confess that we discovered after publishing this theorem that it was in fact largely anticipated by a paper of Stefanov in 2001 that we didn't see until it was too late. So it is in principle in Plowman's work too. Just phrased very, very slightly differently. So the theorem is the following, that while the news may be bad about trapped trajectories and resolvent estimates, while it could be the case that there's exponential growth overall, it turns out that you can always get polynomial growth. In fact, a particular polynomial growth, depending on the dimension. This is almost certainly not optimal as stated, but we didn't pursue that too much. You can always get polynomial growth, provided you excise a very small set of bad frequencies. And that set can be as small as you like. So throw out a set of measure as small as you like of bad frequencies. Off that set, you get this wonderful polynomial resolvent estimate. So actually, from the point of view of a practical numerical analyst, the polynomial resolvent estimate always holds. This was something of a surprise, at least to me. Here's a great picture from Moyola and Spence that shows you why maybe you should believe this theorem. So as I'll explain in a moment, your enemy is resonant frequencies, right? So we all know sort of intuitively that if you have something where trajectories can be trapped, like in your shower stall and you sing, that you hit certain resonant frequencies and the resolvent's bigger, the note's a lot louder. Okay, so here's a partially transparent obstacle, and it's been excited at two different frequencies. You've solved the Helmholtz equation at two different frequencies, and this is the scattered wave from an incident plane wave, technically. And the main thing to take away about this picture is the following. Let's look at the right one. Here's the K for the right-hand picture, and these are quite large values being shown here. The scale, I hope you can read it, is going up a bit above 3,000 at those peak points, maybe even 3,250 or something at the centers of those things. So it's quite large. And now we change the frequency of the incident plane wave in the last significant figure. I don't know how they do this, actually. This seems like an amazing computation. Like, having told you how this works, I'm still amazed they can get this many digits of precision. But they do. They change the last significant figure, and you get this thing on the left. If you've just blown ever so slightly on the frequency, now the scale is on the order of 2. Okay, immensely smaller. So this is sort of showing you that, yeah, the resolvent can be big. I can manage to excite a very big wave from an incident plane wave if I pick the frequency just right, but I really had to pick the frequency just right to make the bad thing happen. So what are the ingredients in the proof of this theorem? And this is essentially what Plowman used too, I think. So the resolvent, let me give you a quick resume of the story of resonances. The resolvent, if I put a cutoff function on either side of it, analytically continues in K to be a meromorphic function. So it's automatically analytic in the imaginary part of K positive, because that stays off the spectrum. But it turns out, and this is a beautiful and deep theorem, you can analytically continue it to a meromorphic function on imaginary part of K less than 0. So there are these poles, it's only meromorphic. Those poles are called resonances. They're somehow, the ones close to the real axis are somehow associated with trapping phenomena. So in particular, it's well known that in cases where there's this stable trapping, like that cavity I showed you, there should be resonances exponentially close to the real axis as the frequency goes to infinity. And so you think, well, this thing has poles in K very close to the real axis. That means it should be big on the real axis. That's why I, and I think almost everyone else, thought, well, the exponential resolvent estimate is all you got, because it's really big, really close to the real axis. But there are a couple of pieces of good news that save you. One is that it's known that there's an estimate on how many resonances there can be. If I take a big ball, there can only be polynomially many for K in that ball. This is for K in that ball. And on the other hand, I also get some bounds on the resolvent away from the resonances in the lower half plane. And they're terrible bounds. They're exponential in 1 over h. That should be 1 over h bar, rather, exponential in K. But they're bounds. And then you can do this beautiful interpolation using what's called the semi-classical maximum principle. I think this goes back to Tang-Zworsky, if I have the history right. It's a kind of finite version of the Hadamard 3 lines theorem. Instead of working in a strip, you truncate the strip, and you have to work in a box and know some decent estimates on the ends of the box. So it's this kind of more quantitative version of the Hadamard 3 lines theorem. It allows you to interpolate between the terrible resolvent estimate you get below the real axis, as long as you stay away from resonances. So say in some little very narrow box where I know there are no resonances. And well, there's a better estimate in the upper half plane because you're looking at the resolvent, the honest resolvent of a self-adjoint operator. And so you know the size is no more, the operator norm is no more than 1 over the distance to the spectrum. So you interpolate these bounds using the semi-classical maximum principle, and you can get some kind of decent estimate on the real axis, which it turns out you can make polynomial as long as you stay a little away from those polynomially many resonances. And that's how this theorem is proved. So I'm 5 minutes early. That's probably a good time to stop and take questions. Thank you.
Thank you very much, Gerald, for the very nice talk. Thank you very much. Are there any questions or comments, please?
Okay, I have a question.
Okay.
Okay, so it's not about those estimates, so it's a different question.
Okay.
So when you take the step size smaller and smaller, you're also changing the shape of those elements, right?
Right.
And what if you take very small size, but they get kind of extreme, I don't know, very long?
I think you're also required to limit their eccentricity. But maybe, say, Francois can bail me out on that. I think I didn't state the full details of like how you're supposed to choose them. They're not supposed to get squished, I think.
Yeah, okay.
Oh.
That's my question. Yeah.
I was going to ask the same question,
No.
and maybe someone can bail me out on this.
Yeah, okay. We need a real numerical analyst for that one. But you're right. All those things I sort of took for granted about how well these finite element spaces approximate things in H1 require certain conditions on how you make that triangulation that I'm definitely not up on, and I would defer to an actual numerical analyst.
Okay.
Yeah, sorry. It can be done. That's all I can tell you, right? If you choose them appropriately.
Yeah, in other words, there are some assumptions there which are kind of hidden.
You're totally right.
Okay.
Thank you very much. Are there any other questions or comments, please? Any questions or comments, please? Okay, Gerald, could you please show us the last slide? I mean,
The
related
last
to
slide
this
here.
argument, I
Okay.
mean, for quasi-optimality. I
All
mean,
right, here's the last slide. It's a little bit brief, so well, all right. I technically have 3 minutes. People are welcome to leave. I'll do it. So this is Schatz's argument. It's really kind of nice. So the first thing, so what is this supposed to show? Remember, the argument is supposed to be that if k eta is sufficiently small, you've got quasi-optimality, or eta is this approximability constant. And so and quasi-optimality, remember, means that you're not too far off from the closest element in the Galerkin space to the true solution, that the Galerkin solution is close to the true solution. Okay, two things. Well, first, this is what's called Galerkin orthogonality. So U is the true solution and UN is the Galerkin approximation, and they both satisfy the same weak problem. So if I pair them with something in the Galerkin subspace, they both give the same answer, which is to say F paired with Vn. So I've got A of U of the true solution minus the Galerkin solution is orthogonal in this rather weak sense to the whole Galerkin subspace. If A were coercive, life would be great, actually. Orthogonality would mean something. But A is not coercive. A is not sign definite, because we've got a Nablus, a gradient squared term and a k squared term with opposite sign. Okay, so this is it looks like orthogonality with respect to an inner product, but that's not really an inner product. Now let's let Fn be the best approximation in the Galerkin subspace to this weak solution of U minus UN. Okay, the thing that solves the equation weakly with right hand side U minus UN. So if I put S star of U minus UN into this pairing, what that means by definition is that this is U minus UN squared. Okay, that's what it means to solve the weak problem, if you think about it. And now by Galerkin orthogonality, I can subtract Fn, because that's in my Galerkin subspace. This is true minus Galerkin, and I can take an Fn out of that right side. And now by definition, since I've taken this best approximation here, this is bounded by my adjoint approximability norm. That's to say, this thing is bounded by some multiple of the norm of U minus UN in H1k. So by definition, this piece can be estimated this way, and then I've also got a norm of U minus UN, just estimating across this bilinear form. So okay, so here's this eta. Now, so let me divide through by the U minus UN here. I get this estimate. So that the L2 norm of U minus UN is bounded by eta times the H1k norm. And so remember, this is like eta U minus UN, well, in H1 dot, the gradient. This is like eta times the gradient plus eta k times the L2 norm. And now if eta k is small, this term is small, and I can absorb it on the left. And so what I find is that actually I've shown that the L2 norm, that this piece of the H1 norm that involves the L2 norm is much smaller than the piece that involves the gradient. So this thing is much smaller than this. And remember, A has a piece that looks like this and a piece that looks like this. And now I've established that one of them is much bigger than the other, that this one's really all that matters. And so I can treat A as if it were a coercive inner product. Okay? And so if I can do that, then here's what I can do by Galerkin orthogonality. I measure the H1k norm of U minus UN, and if A is coercive, I can use that to give an upper bound for that thing. And on the other hand, by Galerkin orthogonality, I can swap UN for WN, anything else in my Galerkin subspace, and now I can estimate this pairing this way. If I divide both sides by U minus UN, I've now shown that U minus UN is within a multiple of U minus WN for any WN in my Galerkin subspace, and I win. That was probably too fast. I mean, that was certainly too fast. It's a beautiful argument. I hope that conveys some of the flavor. You can write it out even rather carefully in a page, and it's very satisfying.
Yeah. Thank you very much. Thank you very much for the nice argument. Thank you very much. Are there any other questions or comments, please? Okay, if not, thank you very much, Gerald, for the very nice talk. Thank you very much, everyone, for coming. Thank you very much. Thank you.
Bye all.